This problem has us find the natural frequencies and the mode shapes for this machine tool that's able to translate vertically and rotate about its center of mass. So in the end, we want to know the two natural frequencies, as it's going to be, and the mode shapes. The tricky part on this problem is going to be in the modeling to see how is it able to move and what degrees of freedom are we going to be allocating here. So there's two ways, well, there's an infinite number of degrees of freedom combinations we could use to explain the state of the system fully, but there's two that are probably the more obvious ways that we could do this. One, and this is the way that I'll pursue it for this problem, is we could say if this is the center of mass, it can travel up or down, and we can rotate around the center of mass as well. So we could have a, what I will call x, and a theta. And if we know the x, we know the theta, we can perfectly describe the state of our system. So those are two independent degrees of freedom. We can rotate it without moving the center of gravity or translating the center of gravity up or down. And we can translate the center of gravity up or down without rotating it. So they are independent of each other. Alternatively, we could choose two different degrees of freedom that describe the state of the system. We could track these 2 points and then call this maybe x1 and call this point x2. Right, so if we hold x2 still, we can hold it at 0 and move x1 up or down. We can hold x1 still and move x2 up or down, and that also would fully describe the state of the system. So that's really just a coordinate transformation that instead of a position and an angle at the center of mass, we could define two positions and still fully describe the state of the system. And we can convert from one to the other, from one coordinate system to the other. So the x1 and x2 together will map to the x and theta that I have going on here. So the pair we choose describes the system, but there is not a unique pair that fully will describe the state of the system. And this goes back to what we talked about in 1 degree of freedom systems. We sometimes had multiple degrees of freedom that were convenient to use in the modeling step, but we had to map eventually to just 1. Here, we can map everything to a set of 2 degrees of freedom that fully describe the system, and then those 2 degrees of freedom are what we're going to use in order to develop our Lagrange equations. And actually, as we go through, I can use both of them, but I'll make a better model out of the 2. Draw its equilibrium state. With its springs and its center of mass, and then I will draw its perturbed state. I'm really going to exaggerate it, even though we're going to say that it's a small angle of deflection here, but that way we can really see how this thing is going to be moving. So this point I will say goes up to there, this point goes down to here, and the center of mass will travel down, or whatever is appropriate for this. So originally, when it's horizontal, that is my value of theta, and then in its perturbed state there, that is the theta that I have passed through. So that's going to be my theta. I'm going to measure x as the displacement of the center of mass, the vertical displacement of the center of mass. I actually will use the x1 here and the x2 to measure how far those points have traveled vertically. Small angles of deflection, so our points are only going to travel tangent to the angle of rotation here. So those are my 2 sets of degrees of freedom, x1 and x2, and x and theta. Ultimately, I'm going to do it in terms of x and theta, as we'll see. But because it's just a coordinate transformation, it actually doesn't matter if I use x and theta to get the natural frequencies and mode shapes, or x1 and x2 to get them. The natural frequencies and the mode shapes are what we call coordinate invariant. And as long as it's a pair of coordinates that describes the system, we're always going to get the same natural frequency and mode shapes. But when we get to the Lagrange equations, we will have to choose one to fill it in as. All right, so let's start with our model now. Let's look at the kinetic energy. The kinetic energy will be in the machine tool that is able to translate and rotate. The springs will have no kinetic energy. So we need to compensate for the translational kinetic energy of the tool. So that will be 1/2 m times its translational velocity, which I am calling, it's the motion of the center of mass, x. So x dot is the velocity squared. Plus its rotational kinetic energy is going to be its inertia, its mass inertia about its center of mass, which we are told is j naught, times its angular velocity, which I am calling here theta dot, and that gets squared as well. Right, so that's the translational kinetic energy of the center of mass and the rotational kinetic energy about the center of mass. Those are the only things with kinetic energy. And now potential energy. We're told to ignore the gravitational potential energy of the machine, so we don't need to compensate for that. But we will have the potential energy in the springs. So let's see here. We will have 1/2 times K1, which I'll label here as K1 and K2, times its deformation. Well, for the moment, I'll use x1 to be the deformation of that point, and that's going to get squared. And then the spring potential energy of K2 and its deformation, I'm calling that x2 for the moment. And that's my v. So if we look at t, we have x and theta, or x dot and theta dot, but in v we have x1 and x2. This only has 2 independent degrees of freedom. If we know both x and theta, we can calculate x1 and x2, and vice versa. So I need to get t and v into the same pair, the same common pair of degrees of freedom in order to do the Lagrange equations. So I will need to do a conversion here, and I will be able to do that using a coordinate mapping or a coordinate transformation. How do I go from x1 into x and theta? How do I go from x2 into x and theta? So x1 is going to be equal to, so notice the way that I have designated x1 positive down. I'm just going to remain consistent with that definition here. So that is going to be equal to, well, let's see. There's 2 modes that cause the translation. If I am just translating the center of mass, x1 and x are the same thing. That is going to be translation of the center of mass, no rotation. So x1 is equal to x, but the machine can also rotate. So I have to superimpose the rotational element that determines x1. So here, by the way that I have designated theta, and let me put in my other measures here, L1 and L2, using small angle approximations here, L1 times theta is going to be this distance. If I make a triangle out of it, that is going to be L1 times theta. However, since theta is I have designated it as positive clockwise, this is actually going to be minus, because when theta is positive, x1 is going to be negative. A positive angle of rotation causes the point to go up in the negative x1 direction. So x1 is x minus L1 times theta. And the similar idea for x2, the way I've defined it, if x is positive, x2 is the equal amount. That's the pure translation. Now I want to think of superimposing the pure rotation. Well, for that, it's going to be L2 times theta is going to be this distance between those points, L2 theta. But this time, when theta is positive, x2 is also positive. So that's going to be an x plus L2 theta. Now I'm going to be able to rewrite v in terms of my x and theta only. So x minus L1 theta squared, and rewrite x2 as x plus L2 theta quantity squared. Now, t is in terms of just x and theta or derivatives, and v is in terms of x and theta. I'm going to expand v out here and going to FOIL this. So I will get x squared minus 2x theta L1 plus L1 squared theta squared plus 1/2 K2 x squared minus, this will be a plus 2x L2 theta plus L2 squared theta squared. All right, so t and v I have in the same pair of independent degrees of freedom. Again, I'll note, I could have done everything in terms of x1 and x2, so I could have converted t from x and theta into x1 and x2 using a similar type of relationship to do that coordinate transformation. That would be fine. I will get the same natural frequencies, same mode shapes. Now I'll use Lagrange's equations. So I want d dt of del t del x. I'll do equation 1. So I'll do x first, plus del v del x. And this is autonomous, so that's going to equal 0. All right, so I can go through my partial differentiation now. So partial differential of t with respect to x dot is going to leave me with mx dot, and then I take the time derivative of that and get x double dot. Plus, I'll put a 0 in here just so I don't forget about it. So 0 times theta double dot, just as a placeholder. Now that second term, when I differentiate t, that goes to 0 because there's no x dot in it. Now, del v del x. So the first term, I will get the x squared will go to 2x and cancel that 1/2. So I'll be left with k1x minus, I have a 2x theta L1. So the x will go away, the 2 and the 1/2 will cancel. So I'll be left with a k1 L1 theta. And then that third term inside of the first parentheses, L1 squared theta squared, there's no x there, it goes away. Now I can move on to that second grouping. I will have there a k2x, the x squared, the 2 will cancel. The 2 and the 1/2 will cancel on the next term, so I will be left there with a k2 L2 theta. And then the third term in the second grouping will also cancel out. So I'm going to rewrite this now. Mx double dot plus, just as a placeholder, 0 theta double dot plus, now I want to group my coefficients, k1 plus k2x plus, and now the same thing for theta, k2 L2 minus k1 L1 theta, and these are autonomous. The right hand side is 0. So that is my first equation of motion. So to get the second one, I will do the same thing, but now I differentiate with respect to my other degree, independent degree of freedom, theta. All right, so my t term, the first term goes away, there's no theta dot, and then the second term I am going to get, I'll put the 0 in here so I don't forget about it, so plus j naught theta double dot. Now the v term, del v del theta. The x squared, that goes away. The 2 and the 1/2 are going to cancel, and I will be left with, right here, a negative k1 L1 x. And then the third term now will not drop out because I have a theta. I will have a here k1 L1 squared theta. Now I go on to the second grouping. The first one drops out. Again, x squared doesn't have a theta in it. I will have a plus k2 L2 and an x is left. And then the third term in the second grouping, I will have there a k2 L2 squared theta. And I want to rewrite this, call it 2a, 0x double dot plus a j naught theta double dot. I'll group my x terms together. I have a k2L2 minus k1L1 times x, plus, and now the theta coefficients, k1L1 squared plus k2L2 squared theta, and these are equal to 0. So these are my two equations of motion based on x and theta being the independent degrees of freedom that I chose. So based on 1a, 2a, I can assemble my matrix form equation of motion. And so I have an m and a 0. When I use vector x double dot, that is x and theta. So m and 0, and from 2a, I have a 0 and a j naught. For my stiffness matrix, from 1a, I have k1 plus k2, and I have k2L2 minus k1L1. And from 2a, I have in front of the x term a k2L2 minus k1L1, and a k1L1 squared plus a k2L2 squared. So these are my mass matrix and my stiffness matrix, K. That's x double dot plus x, and it's autonomous. The right-hand side is 0. Filling in the given information, my mass is in base units 1,000 kilograms. In base units, the mass moment of inertia is 300. So I have 1,000, 0, 0, 300. And then filling in the details for the stiffnesses and the lengths. I was given here, K1 is 3 meganewtons per meter. K2 is 2 meganewtons, L1 is 0.5, L2 is 0.8. Everything I want to put into base units. So if I do all of that, and we'll verify it in MATLAB, I get the K is going to be 5 million. I will get 100,000, 100,000, and 2.03 million. So this way we have numbers to work with in the next step. And we want to double check the matrices that we have formed. Are they symmetric? The mass matrix is diagonal, so therefore it is symmetric. And if we look at the stiffness matrix, the off diagonals are both 100,000. So yes, it is also symmetric. So in our identify step, really we just want to note that it's 2 degrees of freedom and it's linear. That's going to be important because then we know how to find the natural frequencies and the mode shape for this. So the last thing we'll have to do here is actually just the parameter step, because we only need in this problem our natural frequencies and our mode shapes. So we can take our M matrix, our K matrix, and go into MATLAB with them. In MATLAB, I'll put in all of these modeling parameters, just make sure that we get the same matrices that we were just working with. So there's our M, and there is our K, and they match exactly. So we know that for our linear 2 degree of freedom system, or really any multi-degree of freedom system, we can find the natural frequency by taking the square root of the eigenvalues, and the mode shapes are going to be the associated eigenvectors. So just like in previous problems, that's what I'm doing here, is finding those values. Right, so what we have are our natural frequencies, omega n or wn here. I'll print them out again. So our smaller natural frequency, 70.6 radians per second, because everything's in base units. And our larger natural frequency, 82.4 radians per second. And then our mode shapes, column 1 associated with 70.6 radians per second, and column 2 associated with the second natural frequency, the 82.4 radians per second. So putting in the numerical answers from MATLAB, first natural frequency, at 70.6 radians per second. And they did come out in ascending order, and I'll stick with that, 70.6, and then 82.4. And the first mode shape out of MATLAB, negative 0.983, 0.184. And the second mode shape, negative 0.0559, and a negative 0.9984. Right, so that is all that we were asked to find, so I'll put these in the box. But we can go one step further. Now we don't have initial conditions, but we can assemble what will be the start of our total solution. If we did know what the initial conditions were, we could go further. But our x of t, which is going to be our little x of t, theta of t, based on these degrees of freedom, will be C1 if we found it, times that first mode shape, times the cosine of 70.6 plus phi1, plus C2 based on the initial condition, times a negative 0.0559, negative 0.998, cosine second natural frequency, times t plus phi2. This needs a t in it as well. Right, so that would be our assembled solution. If we knew our four initial conditions, we could find the c's and the phi's, but for this problem, we were just asked to find the natural frequencies and the mode shapes. Again, I'll note, I made that choice in the modeling step to have my chosen independent degrees of freedom be x and theta, the vertical translation of the center of mass, and then the angle that it makes. So everything was converted into x and theta in my potential energy expression. However, I could have done this whole thing in terms of x1 and x2. Now, my mass matrix would have looked different. My stiffness matrix would have looked different based on the different degrees of freedom. However, once I got to the step of finding the natural frequencies and the mode shapes, even though m and k are different, I would have gotten the exact same values for natural frequency and mode shapes based on the alternate set of degrees of freedom. So the natural frequency, the mode shape, they are coordinate independent. So like we saw in the 1 degree of freedom system, it didn't matter which 1 degree of freedom we went with. That natural frequency would not be any different. And then if we found the x and the theta, we can go back and we can combine them to find x1 and x2 if that's what we were interested in tracking instead. If we know x and theta, we automatically know x1 and x2. If we know x1 and x2, we automatically know x and theta. So the pair of the coordinates is what matters.